Hello, today we're going to be talking about our Gibbs Phase Rule. This is a phrase that should ring a bell because it's something that we covered extensively in Thermo 1. Let's look first at this theoretical system that's been drawn here. We have two phases of n components, and there is a composition or mole fraction of each component within each phase. It's also at a specified pressure and temperature. Degrees of freedom is a concept that's defined by our Gibbs Phase Rule, and it's essentially a balance between our unknown intensive properties and our correlations between those intensive properties. It tells us how many intensive properties we have to specify before our system is fully specified. For our unknown term, these are all the unknown intensive properties, and the first two that we're going to look at are our pressure and temperature. Within our system, we're assuming it's at thermal and mechanical equilibrium, which means that there is only one temperature and one pressure for this whole system. So our unknown term here is just going to be 2 for pressure and temperature. The other really important intensive property here is our compositions within those phases. Upon first glance, it might look that there are n times pi different compositions here, where pi is the number of phases, in this case 2. But we're looking at what is independently defined by this system. So our nth term within each phase is dependently specified by all the other compositions. We know that the sum of y1 plus y2 plus y3 all the way to n should equal 1. So our nth term is already specified. So really we only have n minus 1 times pi unknowns for our compositions. We show this over here by saying u equals 2 plus n minus 1 times pi. Let's take a look next at our correlations. The most important correlation that we have here is our chemical equilibrium. So this tells us that the fugacity of any component between the phases should be equal. Y1 alpha, or fugacity of Y1 alpha, fugacity of species 1 within the alpha phase should be equal to fugacity of species 1 within the beta phase. If we look at a system with more phases, like this ternary system below, we could say fugacity of vapor equals fugacity of liquid, liquid to solid, and solid to vapor. But again, we run into that problem of one of the correlations being dependently specified. If we know that our vapor is equal to our liquid and our liquid is equal to our solid, we know that solid is equal to vapor. So we can cross that off, and we are given pi minus 1 times n correlations. This is shown over here. We subtract these two terms to get our degrees of freedom. And with a little bit of simple algebra, we are left with f equals 2 plus n minus pi. This should look familiar, as is the Gibbs phase rule that we used in Thermo 1.
Hi, Coop here, coming from the abyss of the black screen behind me to talking about an important condition that Bailey forgot to mention in his Gibbs phase rule derivation. This equation for degrees of freedom is only applicable to non-reactive systems. What these equilibria equations describe is the movement of species between phases. But what they fail to describe that sometimes species can move between species through chemical reactions. How do we take into account reactions with respect to our degree of freedom derivation? Turns out it's pretty simple. All we have to do is add a plus r to the correlations. That plus r represents the amount of reactions within that system. Turns out a reaction is simply a correlation between two species and atoms moving between species to species. So it's a pretty simple fix to the equation. Taking into account the entire end product, all we have to do is subtract that r, because it's a part of the correlations, and add it to the degree of freedom equation. So I wish I could tell you that's the end. But unfortunately, we have to consider certain specifications to a system. Some systems, given for certain applications, right, need important specifications to run properly or to give a desired product. It's also another simple fix, just adding an s to correlations, a specification being one of those correlations. With the current algebra, just minus a plus is a minus, subtract an s from that equation, and that's your end product. In a moment, Max will take it over and give you an equation and an example of how you can apply it.
Hi. Earlier in this video, you've seen a derivation of the Gibbs phase rule for a reactive system. That's very helpful, except we haven't looked at a real situation in which this will apply. Let's look at the system we have here. Here we have methanol decomposing into formaldehyde and hydrogen gas. Note this system is all gas, and it's an evaporated flask to start with just methanol. This is very important, and we'll find out later. First, let's look at the phases we have in this system. Obviously, it's all gaseous, so we're just going to put 1 for phases. Let's look at our species. We have 1 species to start, but with this new reactive system, we have 3 species total, and we're going to assume that all 3 of those are present at equilibrium, which is very important. So we're going to have 3 species. Next, let's look at our reactions. This reaction is reversible, which one may think that means we have 2 reactions. However, we just have 1 because it has to be linearly independent. If we had 2 reactions, but one was a multiple of the other, then it wouldn't be applicable. So we just have 1 reaction. Next, let's look at our specifications. Because this is an evaporated flask, CH2O must be equal to H2O. If that isn't clear in your head, then just imagine 1 mole of methanol reacting to form 1 mole of formaldehyde. For every mole of formaldehyde that's formed, you have to have 1 mole of H2 because it's an evaporated flask. It has no other source. So that is why we have 1 specification. If we apply this to our equation we already derived, we have 2 plus 3 minus 1 minus 1 minus 1. That puts us at 2. That means our degrees of freedom is 2, which means we need to specify 2 intensive variables in order for this system to be fully specified. Now, one may think this is just some random rule that gives us insight into the system itself. However, if you have a system and it could be very complicated to solve for certain variables, and you don't assume something in the beginning, well then this tells us if you need to assume something, because if you get halfway through the problem and you realize you can't solve it, that doesn't help you very much. Thank you for watching.